I am Jake Bernstein, and this is Lab 5, Choose Your Own Adventure. I've decided to analyze the motion of a falling slinky. Now, on the agenda for today, we have Part 1, the introduction, where I will be discussing the purpose, key concepts, and applicable formula, as well as the setup. Then we have the tracker analysis, as well as the computational model, the comparison between the two, and then finishing up with our discussion and conclusion. So the purpose of this lab is to verify physics principles acting on a stretched slinky dropped from static equilibrium by comparing this motion to the motion predicted by our computational model. Now, the general motivation behind this is to answer the overarching question of, does the bottom of the slinky remain stationary during a specified period of time, and then why? Does it or does it not? And then a preview of the results is that the concepts surrounding the momentum principle were corroborated by this lab, as evidenced by the computational model. Now, some key concepts we'll be touching on in this lab are Newton's second law. The change in momentum of the slinky is proportional to the net force acting on the object. That's been a recurrent theme over the course of these past 5 labs now. Secondly, we have the drag force and the force of gravity, both pretty self-explanatory. Now, just 3 key formula that we'll be using today: the velocity update formula, the position update formula, and then the drag formula, all on screen right now. Now, the setup, as we can see, we have these 2 men from the YouTube video, one holding the slinky, which is our system today. The surroundings are the Earth and the men. And tracker calculated the mass of the object to be about 0.21 kilograms, 210 grams. The initial position is that very small x component and that very small y component. And the initial velocity obviously is 0 as it starts from rest. Now here I'll play a video of the tracker analysis for you. Right here, 2 times speed. We can see the slinky fall. The bottom appears to be at rest until that point as it falls down. So now we attempt to generate this motion of the slinky in an application called GlowScript. And first, we have to define the ball's mass, as seen there, the position and velocity vectors, as I went over 2 slides ago. And then gravitational constant is 9.8. The constant of the drag force was determined to be about 0.5. And then our j hat is in the positive y direction. So the next 2 bits of code are both while loops. The first one is basically the time from when the top of the slinky is falling down and compresses into the bottom of the slinky, and that's 5.67 seconds, just about. And then after that, we have the second while loop. Now, you can go through the code by yourself and see the structure of it, but the main difference is that in the code to the left, the net force is just the gravitational force, and then the opposite of the gravitational force, which is the tension in the slinky. But the second one accounts for the drag force too, as the object is falling. And then we just calculate the velocity and the position using the update formulas that were touched upon just a few minutes ago. Here are our results. And as you can see, plotted in the red and the blue, the computed position generated by tracker very closely mirrors that of the observed position, which generally is a good sign and points towards a successful lab. So that brings us to the conclusion, and I'll read this for you here. The overarching principles surrounding Newton's second law were corroborated by the results of this lab. Now, we were able to accurately model the motion of the falling slinky by means of the tracker software, doing so by leveraging our knowledge of the applied physics, the modified position and velocity formulas. Now, most importantly, the bottom of the slinky stayed stationary in the air during the duration of the compression, and I'll go more in depth into this on the next slide in the discussion, but this is basically due to the tension in the coil negating the effect of gravity. Now, some potential errors are human error, most, obviously being the inaccurate tracker analysis, because I had to manually place the plotting software. And then the second one is the influence of surroundings, meaning that there could be external forces acting on the object that weren't accounted for, being the wind or the man's hand, whether he held onto the slinky or even applied force downwards. We can't really tell just given by the video. Lastly, our discussion, we have 2 questions here. Why does the bottom of the slinky remain stationary? And I touched on this a little bit ago, but the slinky acts as a type of spring, and the internal tension in the slinky counteracts the force of gravity, as seen from 0 to about the 5.67 second mark in the computational model. Second question is, what happens if we put a large weight at the bottom? Would the slinky still remain stationary? And this is a little more complicated, but as long as the tension force counteracts the gravity, the station will remain stationary.